Good day, viewers. Good day, everyone all over the world. Welcome to Cayman Physics Tutorial. Today, we are going to be doing something special, as you can see on the board. So what we are going to be treating today is something very unique. In respect to what we have been treating for a while now, in my last video, I talked about dimensions, and I've taught you how to check if a formula is dimensionally correct or consistent, right? So, and I've also taught you how to find the dimensions of various constants. That was what I did in my last video, right? So, in the last video, we were able to look for some constants in physics. We checked some constants in physics and we found the unit, the derived units, because we have two types of units now. We have the fundamental units, which we also regard as the basic units, and then we have the derived units. Since we derived a unit for those constants, physical constants, so we name it a derived unit. And how we do that is very simple. If you have not watched it, go to my YouTube channel, go to my Facebook page, Cayman Physics Tutorial, and check the last video uploaded on it. Subscribe to my YouTube channel, then you click on the notification, and so that when we release any video, you can be notified. All right. So today we are doing something different from that, right? Today I'm still going to be using the idea of dimensional analysis, which we usually use in physics. So what I'm going to be doing today is how to create your own formula in physics. I'm sure you have been anticipating to know how are all of the formulas we see in physics, how did they came into existence, right? How did they come into light? How were these formula created, right? How they were created is how I'm going to show you right now, right? Although experiment foresight must have been done for any formula to have any scientific justification, right? So let's assume that you go to the lab, you do some experiment, you perform any experiment, and then you came up with some parameters. And then the parameters at which you came up with, those parameters are the parameters you came up with are very useful to you, right? And you want to form a formula out of it. You want to create a formula out of it. You know that these formulas I have created for my experiment so far, my experiment is correct, my data are correct. I'm sure of this new thing I'm getting. And I want to be able to connect these formulas together to see what formula can I create out of these parameters that I've gotten. Right. So this is the same way that we usually create formulas in physics. So today I'm going to be showing you two questions, and the questions is what I have here, right? So we can take this as 1, and then we take this as 2, right? So these are the two questions that we are going to be looking at. But I'm going to be solving the first one for you. I'm going to be showing you how the first one is being solved. I'm going to solve that for you. And then the second one is what you are going to be doing for yourself, right? So I'm going to give you some hints about that when I'm done with the first one. Then you see how it is being done, so you can continue with the second one for yourself. I always like to give people what to try, right? So once you notice, each time I teach you something new, I'm going to give you something to try, because I know you only understand it better if you lay your hands on something. So always do well to lay your hands on whatever question I send to you here, right? So good. So let's begin with the work for today. If you check what we have on the board, let me copy the question, and then I can paste somewhere else. Right. So I'm going to paste on a new page. Right. So this is the question. And we are just going to start now. This question talks about an hydrostatic pressure P of a particular liquid column, which depends upon density D. and the height of the liquid is represented by h, and the acceleration due to gravity is g, as we all know. Then they are saying using dimensional analysis, you should derive the formula for the pressure. This is a formula that we all know, that we all have been using. It has been proved, it's viable, it's consistent, it is correct, and we all know the formula, right? But what I'm going to be doing in this video is this. I purposely chose this question because I want something that has been widely accepted, something that we can be able to justify, something that is already proven viable, right? So we all know this formula. Assuming you are the one that performed this experiment and you saw that these parameters depend upon each other. You can see they said the pressure probably depends upon the density, the height of that liquid, and then acceleration due to gravity. So those three parameters depend upon the hydrostatic pressure applied, between the liquid column. So if you have done an experiment like this and you have the relationship this way, you must be able to have the relationship, right? You must be able to have the relationship between the independent variable and then the dependent variable, right? So from here you will have seen what is dependent and what is independent, right? So once you have this and you want to see how these three, how many parameters do we have again? Now 4 parameters, right? 4 variables: P, pressure; D for density; H for the height; then the G for the gravity. So 4 parameters now is what we want to connect together. We don't know what the formula is going to look like, but the secret here is this: dimensional analysis will give you the formula. If you solve it correctly, it's going to automatically give you what the formula should look like. And that is why we use dimensional analysis to create formulas in physics. If our experimental result is correct and we know what is the independent variables, we know the dependent variables, we put them together and we derive a formula, right? The formula you're going to prove, for this one, we know what the formula is going to look like, right? But in most cases, you don't know what the formula is going to look like if it is your experiment, because you are doing something new, right? The first person who did something like this, those guys that worked on something close to this is Archimedes, Pascal, right? Archimedes, Pascal did something as close to pressure and atmospheric pressures and hydrostatic pressures and something around that. But these guys don't know what the formula is going to look like until they were able to apply dimensional analysis and other methods as well. But in this video, I'm going to be focusing our attention on dimensional analysis. Very simple for you to be able to attempt. So now I'm going to start. The first thing to do, if you want to start that, the first thing to do is you need to know what is depending on what, right? Firstly, they have told you that the pressure depends on the density. You can just simply say that the P is directly proportional to the density, right? That same P again, you can see, is directly proportional to the height. The same P is directly proportional to the gravity, right? To acceleration due to gravity. So if you look at these 3 things, you don't bother yourself because you feel like, oh, how do I know if this is directly proportional? Why is it not inversely proportional, like indirect proportionality? So you don't have to worry about yourself about that. If this is indirect, if it is direct, automatically the formula is going to rearrange itself at the end of the day. That is the work of dimensional analysis, right? So, but you just make it a direct variation, make it direct variation. But in all of the parameters you have here, in all of the parameters, you need to make it dependent on something, like give them variables, right? So you need to give them variables, like let's use x as a power here. Let's use y as a power here for the height. Then let's use z as a power for the gravity. So you understand what I'm saying now. So this is like the density, right? This is the height, and this is the gravity. So you know those 3 parameters, that it depends upon the pressure. That's the P you have here. the P you have here is the pressure, right? So now, having done that, that is the way to start. But we can always connect these three parameters together. If you connect these three parameters together, it's very easy to connect. Connecting those ones, by connecting, you are going to have the P to be directly proportional to the distance, the density, I mean, directly proportional to the density. We usually use D as the distance, so I missed that. We usually use rho for the density. So, but let's since the question says we should use D for density, so no problem. Let's just use D for density. So the height, and then directly proportional to the. So don't forget what's upon them. You can still make it your X, your Y, and your Z. Right? So these things can be joined together. If you join this together, it's going to give you directly proportional to the D, H, and G. Right? So you can still give them the X, Y, and Z as the power. Right? So once you have done that, once you remove the proportionality sign, something is going to be introduced. Then what is going to be done is the constant. We did that in the last video. If you have not watched that, please go to my YouTube channel or my Facebook page. The last video that we uploaded, go check it and watch it and watch the video, and you have a better understanding of this. Right? So connect this together. You are going to have P to be equals to K, D, H, G. So you can still repeat your parameter, your variables, X, Y, and Z on those variables on the right hand side, right? So once you have this, you know what the K is doing. The K, we don't know what the K is right now, right? So, and that is one of the difficulty of dimensionality and dimensional analysis. We don't know what that constant is always. We do an experiment, you still have to go back to the lab to check what that constant is going to give us, right? But we are going to see what the formula will look like. Just that we might have to take the K as 1 at the end of the day, right? But in some cases, the constant is not always 1, please. The constant is not always 1. You need to go back to the lab and check, do some experimental work and see what the constant is going to look like. But in this question, we all know the K is equal to 1. In some cases, it's going to be 1, right? So regardless, we are going to see what the formula looks like at the end of the day. So this particular formula, you can just call it let's call this one equation 1 so that we can always refer to it, right? Let's call it equation 1. So we can always refer to this equation, right? So good. From here now, there is a particular law we are going to apply right now. And that law is a law we call the principle of homogeneity. Principle of homogeneity. So if you apply the principle of homogeneity, so you are going to have a particular result. The result is going to be coming out from equation 1. Don't forget that it's equation 1. So very simple. What the principle of homogeneity is saying is that you need to be able to, it's telling you that you need to be able to treat each of these as a separate quantity, right? That's what the principle says. The principle says treat each of these as a quantity and write them in their, each of this quantity, like the pressure, density, height, and gravity, should have their respective dimensions. So that's what we are going to be doing. So if they need to have their own respective dimensions, what we are going to have is, as a result, we are going to have P, if you notice. So let me just write it out. That means that P is going to give us the K constant won't come in now, right? You leave the constant out of this. D, H, and G. And don't forget your X, Y, and Z. So you need to be able to write these ones now in as, right, the dimension, as dimension. I think I better use, so you can see it well. Let me just use a different pen. Right. 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 Good. So this is what you are going to have. Just have a big, square brackets around each of the variables. So once you have this, and then you still have your variables can still be written on it. You can probably write that one outside so that it doesn't confuse you guys. This can be X, this can be Y, and this can be Z. You can write it outside, right? So once you have been able to do that, good. The next thing now is you can supply your dimension. So to find the dimension now, you need to probably we make this equation 2 so that we can all go to find the dimension, right? We can go to obtain the dimension of each quantity, right? So we can find the dimension of each quantity, that is the pressure, the density, the height. So let's quickly go through that. If you can quickly go through that, for those who are not familiar with that, we can just do that very, very fast to show you guys how that is being done. We have been doing that for a while now, right? So what you do is, you write the formula. The first one is pressure. Pressure has a general formula which we all know. That is force all over area, right? You can denote this by F and denote this by A, right? So, and the F you are seeing there, we have been able to find that one as MLT minus 2, right? The area, we have been able to write that one as L squared. You see that? So putting those things together, the pressure P can actually give us MLT minus 2 all over L squared, which is probably going to, you're going to a new one, you have one L left. So you are going to have the P to give us M. I always write mine in terms of MLT. So that's the arrangement I have. When this L goes up, we are going to have inverse, then T minus 2. So this is one. This is one, the pressure that we can put inside of that. I'm talking about this. So we have got that. This now, the pressure has been the same thing. Do the same thing for density. If you do the same thing for that as well, you are going to have, for density, same thing. You know what the formula is going to give us. That is, for this case, we usually use rho, but for this case, we are using D. So stick with it. That is, the formula is mass over volume. So which we usually have M over V, right? So the mass here, you know what the mass is going to give us. The mass M, the dimension is going to be still capital M, or you differentiate it, right? Then for the volume, that is still going to give us length, breadth, height, which is like length times length times length. That is L cube, right? So if you put these two together, you're also going to have the density now, which is going to give us D. You put the mass there over the volume. That's going to give us M, right, all over L. This is what you are going to have. But you can move this up to make it linear. So therefore, you are going to have the D to give us M L raised to power minus 3. Because when the L cube goes up, it becomes a negative. So you are going to have here this. So you can as well put, right? We can as well note this such that we can come back to it later, right? So you see, that is how we have the density as well, the mass over the volume. Then we did the mass here, we did the volume, then we put these formulas together, and then we have this as our result. So the next one to do, if you in the formula, if you notice, now we have been able to do this density. Now we are able to sort this out. The height, that is going to be very simple because that is just taken as length, so we don't need to waste time on that. So we can say that the height h is going to give us just L. That's all. It's regarded as length, right? So you can just conclude that h is equals to L, and that is all. Right, so that is the third one. And then the last one, the last dimension in the formula that we are going to be looking for, we have looked for the pressure. If you look at if you follow me on, we have looked for the density, we have looked for the height, then we look for the gravity. Don't forget that gravity, you need to go back and check is what we are talking about, the gravity here, which we always call the acceleration due to gravity. So this is just an acceleration as well, but this is not due to motion. An acceleration can be due to motion, right? Can be due to gravity as well, right? So like free fall. So this is an acceleration that is due to gravity. So we are now going to find that one, and we are going to treat it just like acceleration, right? So we all know that the dimension for the acceleration the small g is just going to be treated like acceleration, right? Which is LT minus 2. So in a way, you are going to have the g to give us LT minus 2. Just like that. So it's just treated like acceleration. You can use several means. You can use several means to confirm that. One way to confirm this is if you say F equals to mg, then from here you can find the g. If you say F equals to ma, you will be able to find the a, which we can now take as g as well, right? So whichever one you are looking for, you will be able to get your answer as LT minus 2. So now if you check, we have been able to get the 4, this is the first one, right? First, second, third, and then the pressure itself. So we are now going to put all of those dimensions we have gotten into this equation 2, right? So I'm going to write that equation 2 below now, and I'm going to put what the pressure is, the dimensions I mean now. That is the principle. What is what the principle of homogeneity is saying. We put the pressure in, the dimensions of the density, the dimension of the height, and the gravity. So you put those things into it, right? Let me just write that one out. So in a way, you are going to have, if you recall, P, we took P as D, right? height, and gravity, right? So where we had this as x, y, and z, right? So putting those dimensions into it now, you are just going to be carefully substituting those things inside of it. And there's something to do there. We follow anyhow you want to arrange it. You can arrange it just anyhow you want, right? But the most important thing here is you need to be able to have your mass, length, and time, because those are the three important things that you are having here. The longest formula we have here is the pressure, which has the mass, length, and time. So wherever you are not seeing the mass, length, and the time, such as there's no time here, right? Just take the time raised to power 0. Look at this now. There is no mass here. You can take it as raised to power 0. There is no time here. You can take it as raised to power 0, right? So that we can balance the right side and the left side. We have the length here. Good. We have the time here, but we don't have the mass. We can take that one raised to power 0. Of course, that is an in indicial law, which says that anything raised to power 0 will give us 1. Any variable raised to power 0 has been proved to be 1. So just use that one to make it 1, right? So if you take if you're taking the pressure, if you substitute the pressure, is going to give us m l raised to power minus 1 t raised to power minus 2. So this will be 1, which will be, is going to give us mlt m raised to 1. If you go back and check, I just added 1 here, right? T raised to power minus 1, then t raised to power minus 2. So t raised to power minus 2, L raised to power minus 1, right? So the next one is the density now, right? Which, if you come back again, I'm just being careful so that you can check well. M L raised to power minus 3. That will give us m L raised to power minus 3, but you can just take this as 1. Then you can add your t, which will be raised to power 0. It doesn't make any effect there. For the third one, which is the height, that should give us just length, right? So that means that the m here is going to give us 0, right? The L here and the t. The only thing that's going to count here is the length, right? Which is going to give us 1. This is also going to give us 0. There's no time in that, and there's no mass in the height. So the last one, you are going to multiply. By that, there's going to be a multiplication sign there. Don't forget. So the last one that you are going to be treating is going to be the gravity, which is going to give us something as LT minus 2. But you can still put your m there, right? As 0, L as 1, T minus. So each of these now has, but don't forget, we usually have some variables that we started with already in equation 2 and equation 1. Equation 2, those variables that I wrote here, your x, y, and your z. You need to come back and put those variables outside of whatever you have there, right? You need to come back and put it there, so such that, and you know that these variables are just on your right hand side. So you are going to have the x, the y, and the z, right? So those three variables, those are the things you are going to have there. So the next thing to do now is just to bring in all of the x, y, z on all of the on the right hand side. On the right hand side, just the way of indices, whatever variable we have outside, we multiply what variable we have inside. The powers outside the bracket and inside of the bracket can actually multiply. I'm talking about this x can multiply this can also multiply this, that same x can also multiply this. The same thing, this can multiply this, that same y can multiply this, and that same y can multiply this. And this also the same thing, multiplying 1 and then multiplying this. So if we do that, you realize that you'll be left with some quantities that we can actually eliminate from there, right? So follow me on and see how I'm going to solve that now carefully. The left hand side does not have any problem for now, so just drop it. So you are going to have M L, I'm just repeating the pressure, T minus 2, just like what we have there. So the first one is going to give us, take the x, the one that the power of x, use it to multiply. You are going to have M x L minus 3x, then T. If you use that to multiply the x, you are still going to have your 0, right? So please note that. Multiply it times the second one, which is this, right? So we are going to have, we are multiplying times y. It's still going to give us 0. It's going to give us y. Then it's going to give us, the t is still going to give us 0 if you multiply it. So you are going to have this. Then for the third one, that is the, I'm talking about this now. You use the z to multiply each of the powers. So you are going to have, at the end of the day, you are going to have m multiplying times z, because you have 0 there. You are going to have your 0 back. This one, more 1 times that, you are going to have the z. Then the t, you are going to have minus 2z. So please don't mistake that. Let me write it well, so you don't mistake that this is 2 and this is z, right? So you can close that now. That's what you are going to have. All right, so this is what you are going to have at this particular stage, where you have been able to bring in all the powers inside. You bring in all the powers inside. You can see the powers we now have now is in terms of variable x. This is in terms of variable y, and you know that. So at this stage now, here is a good time to eliminate whatever is going to turn to 1, right? For example, this is going to turn to 1, right? This is also going to turn to 1. This is also going to turn to 1. This is also going to turn to 1, because even after introducing the variable inside of our dimensions, they still have no variable on them. So which is variable having a power or an index up to 0 is going to be turned into just a single one. And if whenever one multiplies this, you know what we are going to have. So in short, we are going to have something like this, right? So we are going to have something like the left hand side as well. We are going to have M, L, and T. That is the left hand side. Let me write the right hand side now. So you know what is going. This is going, 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 and going. They will all turn to 1, right? So from there, you are going to be left with, now we have a space here, M, X, minus 3x. That's what you have there. So you are going to multiply that. The second one, just y, that is L raised to power y, right? So you multiply it for the third one. That one as well, you are going to have just the L, and then you are going to have t raised to power minus 2z. That is what you are going to have for that particular stage, right? So step by step, if you follow me through, you see that I've been able to remove whatever variable is going to turn to 1, because m raised to power 0, t raised to power 0, anything raised to power 0 here is going to be 1. So now I'm left with variables that have at least 1 as their power, or they have like a variable as their power, right? So once you have done that, the next thing to do now is, the complex aspect of this thing is that we need to balance, we need to have equality in whatever we are doing. This equation right now is not equal if you see it. this equation is not equal. So what we simply do here is we equate the left hand side to the right hand side. Equate the left hand side to the right hand side. So basically that means that you are going to be matching the right hand side, because the left hand side has no problem. You have your MLT already. So on the right hand side is where the work is right now, right? So we can just say that solving the right hand side, right? So from there we are going to bring all of the m's together. That means that the m is x, right? So let's bring the next thing is L. Let's bring all the L together. The L we are going to have here is L. The first one is having the power of minus 3x, right? The second one, we are multiplying it. The second one is having the power of y, right? And then the third one is having the power of z. So, right. Then the last thing you are seeing here is your t, right? So then you multiply again by your t you have here. So we have done the m, the 3L has been matched together. So the last one here is your t, which you are going to bring in now, right? So you have your t raised to power minus 2z. Then you close this. Don't forget, I only matched and compress the right hand side. The left hand side has been left for now. Once we are able to sort out the right hand side, then from the right hand side we'll bring it onto the equation back, then we'll continue solving. But let's match this together. You remember what happens to these 3 powers because of the indices sign we have, right, in between them, because of this and because of this, right? So they are going to turn to plus. They're going to turn to additions to the power. They will become additions to the power, right? It will become a plus sign. So the plus sign will now make them have just a single length, a single L, right? So in a way, you are going to have m raised to power x, just a single length, which is 3x plus y plus z. Then your t can be written last there, right? So that is what you are going to have for that, right? So that is what we are going to have for the right hand side. Don't forget what I've just done here is the right hand side, right? This is for the, let me put it there, right hand side. So this is still the left hand side. The left hand side. So I've just compressed because of this lengthy ones that we have here, I brought it together here and then I apply indices to it here. So that is all I have done. So you can now make the left hand side to be equals to the right hand side, right? So if you equate the equation, if you equate the left hand side, right, if you are obtaining the equality, let me just say obtaining equality on both sides. So what we are saying there is that we want the left hand side to be equals to the right hand side. Since we have been able to have just single 3 variables on the left, which is MLT here, and then we have the MLT here, right? So they can now be equated. So on the left hand side, don't forget what we have been having. On the left hand side, we have been having M1 L and then T minus 2, right? So you can make that to be equals to the right hand side, which we just did now. That's going to give us, if you look at it, M is to power x, L minus 3 plus y plus z, right? Then T raised to power minus 2, T raised to power minus 2z, right? So this is the left hand side, and this is the right hand side. So what we have been able to achieve here, if you notice, we have been able to achieve something here. What we have been able to achieve here is that the left hand side now has now been equated to be directly equals to the right hand side. Apart from that, you see that just three variables have been are what we have here. What I mean, three dimensions, three variable dimensions, which they have their powers, like the mass, length, and time. On the right hand side as well, we have the mass, length, and time. So these are the things you must be able to do. We don't have two length. Once we have that two length, merge it together by the law of indices. Very simple, right? So it's possible we are going to be having two length, three length, or two time, two masses, three masses. Very simple. Just collect them in like terms, and then you apply indices and get whatever you have there. So the next thing to do here is that we are going to be equating it. Since we are saying that we are equating both sides. Equating both sides means that the power of m on the left hand side can be equated to the power of m on the right hand side. The power of L on the left hand side can be equated to the power of L on the right hand side. So since we have just three major dimensions here, which is the mass, the length, and the time. So we can just bring their power. The power on the left hand side can be equated. So the power on the left hand side of this one, which is 1. If you notice, 1 here. But on the right hand side, it is hex. So in short way, you can say 1 is equals to hex, or hex is equals to 1. You have been able to find the value of hex like that, as simple as that. For the L as well, you say -1 is equals to, then this is -1 on L here will give us the whole of this, right? So you are going to have -3 plus y plus z. That is what you are going to have. Then for the third one, which talks about the time, right? Which is on the left hand side, you have -2. On the right hand side, you have -2z. So if you write that out, it's just telling you that you are going to have -2, which will be equals to -2z. Right. So out of these three equations, you have to solve these three equations to be able to get those variables that we used at the beginning. Right. So you need to solve these equations for you to be able to get the value of the x, y, and z. It is not that same value of x, y, and z that you go back and present and substitute back into equation 2, which will now, or you put it into equation 1, the earlier equation, the first equation 1. That's now the equation that will now tell you how is it going to have a square? Is it going to have whatever you do there is going to, whatever we get here is going to be power to those equation, to that particular equation. So very simple. We have been able to get x. It's very simple for us to get z from here as well. From here you can easily find your z. You can find your z from there, right? So since -2 is equals to -2z, right? From here you can decide to divide both sides by -2, right? So you have z to also give us 1. So when these are known, we are going to have a 1, right? So now if you see it, we have been able to have x is equals to 1, z is equals to 1. So the next one is to use this equation to get just substitute your value of your x, right? Value of your x, value of your z, then you can obtain the value of your y, right? So you can write that equation out, then we quickly do that. So in short, that equation will look like this. That equation is -1 from -1 is equals to -3x plus y plus z. right? If you put your value of x here is 1, your value of z here is 1, so you can find your y. So it means that x here is 1 and z here is equals to 1. So if you do that, that will give us -1 is equals to -3. Your x there, you are going to have 1, right? I've substituted 1 into that x. Then you continue again, plus y, plus, then you put your z again, which is also 1. Right? So what we are presently looking for now is that we are trying to look for the y. We have not gotten the y. So how to get this y now? Very simple. You just compile it together and you find what your y is going to look like, right? So the y here is going to be, if we solve that together, let me use a pen. If we solve that together, that's going to give us -1. This is -3 plus y plus 1, right? That's going to give us -1 is equals to this, and this can come together, -3, then plus 1, you still have a negative 2, -2 plus y, right? So you can move that to outside. That is -1 plus 2 is equals to y, right? So your y here can give us a -1, then plus 2, right? So you are still going to be left here with your y giving us a 1, right? So here you'll be left with your y giving us 1 as well. So you can just conclude and say y will give me 1. You see that? So if your y is giving you 1, we can also like put this together. So you can see here we have been able to see that the x, which is the most important thing we have been looking for, is 1. The z as well is 1. Then the y also is 1, if you see that, right? So now we can put those 3 things together. Those are the major things we are looking for, right? So finally, x is 1, y is 1, and z is also 1. So we are now going to write the original equation 1. We are going to write back the original equation 1, the one that has the constant, proportionality constant k there. Put all these variables, x, y, and z, as powers. Put it there as powers, then you see what the equation becomes, right? So let me go back and show you the equation, then we pull it. Let me go back and show you what the equation is. This is, yeah. So this is where we talked about the relationship between those and the pressure. And this is the equation I'm talking about, equation 1, right? So it is this equation that we are going to work with, right? So that is the equation we are going to work with. That particular equation is what we are working with, right? So we can copy that, and then we can go paste it, and then we will insert the variables x, y, and z. So we can paste it, right? So this is what we are working with now, right? This is the equation. So you now know what this is how the equation should look like. But now you know what your x, y, and z looks like. So if you substitute your x, y, and z into that equation, you are going to have P, which is the pressure we are looking for, to be equals to the K, the D. Then we know this is raised to power 1. right? We have the H. We know this is 2 is going to give us 1, right? Then we have the G as well. The G. Let me make this uniform. Then we have H and G. So putting back what X, Y, and Z means, which is going to give us 1, 1, and 1 as a value. So which is still going to give us the same thing, right? So we can now say that the P that we are seeing here is K, D, H, G. That is what the formula is going to look like. That is what that formula is going to look like. I can rewrite it here to show you. We are going to have the pressure is constant K, density H, and the G. So that is going to give us something like this. Right. So this is the final you are going to have. But it has been proved. Like I said, you need to go to the laboratory to check what you are doing, right? To do some experiment and see what is going to be the value of my constant. The constant is not determined by dimension analysis. You can't find the dimension using dimension analysis. Please take note. So, but for this particular question, we all have been saying this. If you take D, if you take the D there as rho, you will have been familiar and seeing this question that says K is equals to rho Hg. You will have been saying this. You will have been saying that particular you will have been saying that particular formula. If you have been familiar with physics, you will have been saying this formula, right? So the K has been proved to be 1, right? We are not the one. The formula has been proved to be 1. K is 1. So if the K is 1, the final answer here is going, since we are using D, so let's continue with our D. The final answer here is going to say that P is equals to D, H, G. That's what the formula is going to look like. This. So this is going to be our answer for that. This is going to be our answer. So you can see now that even without knowing what the formula is, you can prove the formula. And that is how this formula was derived. This is how the formula was dimensionally proved, right? So what I want from you guys now, I'm going to go back to the question at the top, right? I'm going to go back to the question. I'm going to place it at the question. You can take the question down. And this is the question. This is the second question. Yes. So I've been able to solve this for you guys. Say the pressure, the density, the height, and the gravity. We have been able to treat these things. But now you are to try this. Right? So try this. You see, they have even given you what the formula should look like. That's what the formula should look like. And for this case, the K is not 1. It has been experimentally proved that the K is not 1, right? So not to confuse you and just put K there. They have told you the K here is 6 pi, right? So you are working between these 3 parameters. And then I purposely brought out these questions because of the coefficient of viscosity, which I treated in my last video, right? So if you have not watched the video, please go and watch that video. Watch the video and see what is called the coefficient of viscosity. See what dimension the viscosity has. That is where to see the dimension of that viscosity. You substitute here and you solve just what I have done here. Apply the law of homogeneity, apply the equity law, and then solve down, merge, do some substitution, some little equations. Sometimes it leads to simultaneous equation, right? You solve those equations and get your variables, whether X, Y, Z, whatever you are going to use, and depending on the quantities that you have, right? So ABC or whatever you want to use to represent your variables. So once you have your variables, you put it back into your original equations and you see what your equation is or what your formula is going to look like. So that is what I'm going to bring to you today. That is how we usually check and how we usually uh, prove a formula. That's how to create a formula for yourself. So I've just given you a secret on how to uh, bring up and form a formula for yourself, right? So